welcome back. This is Mrs. Rubright with Algebra 1 Honors. Today's lesson is 6-2, Rational Exponents. Alright, so, understanding real numbers and their properties. The Venn diagram shows the relationship between the set of real numbers and its subsets. Okay, so we have real numbers. So what are real numbers? Real numbers include our rational numbers and our irrational numbers, okay? So we have the set of rationals and the set of irrational numbers. So, what is an irrational number? So an irrational number is going to be like pi. It never terminates and it never repeats, right? 3.14, blah, 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 blah. Goes on forever, never repeats, right? Never ends. If I did the cube root of 2, cube root, I get 1.25992105. It's going to go on forever. It never repeats. It never ends, okay? If I did the square root of 10, the negative square root of 10, negative 3.16227766, it is going to go on forever. It's just the calculator doesn't fit that many digits, but it will go on forever. It never repeats. It never terminates. It never ends, okay? So it says an irrational number cannot be written as a quotient of two integers. Its decimal form is non-repeating and non-terminating. For instance, the square root of 3 is 1.73200508. It neither repeats nor terminates, therefore it is irrational. So irrational numbers never repeat, never terminate. They never end. So, if that's what irrational are, then rational must either terminate or repeat. They either terminate or they repeat, right? So, 2/3. 2/3 is point what? 2/3 is what? 0.6 repeating, right? It repeats. 8 divided by 17. 0.47058823. Can't really tell from the calculator. They didn't give a good example. But it's supposed to either terminate, like end, not go on forever, or repeat. All right, so let's go into the middle, so whole numbers. Whole numbers are like your counting numbers, right? So it's going to be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a million, 100,000, right? All those whole numbers, including 0. They're kind of like your counting numbers. Right? Your whole numbers are like your counting numbers. They're starting with 0, going on up. Right? Integers are whole numbers and their opposites, so it includes the negatives, right? It's whole numbers and their opposites. Right? So that's all your whole numbers plus the negative versions of them. All right, and then we have our rational numbers. So your rational numbers include your whole numbers and your integers, but also those fractions like 1/2, 1/4, 0.4, 0.2, negative 0.25, negative 0.3 repeating, negative 0.123 repeating. So it either repeats or terminates. It includes positives and negatives, right? Fractions and decimals. Are you guys okay with the categorizing of your numbers? All right, so if there's real numbers, what's the opposite of real numbers? You're probably going to say fake numbers. Your fake numbers are called imaginary numbers, okay? So you have your set of real numbers, and then the opposite side of that would be your imaginary numbers. So your imaginary numbers that you'll get into in future math classes, those are going to be numbers like the square root of -4. So the square root of -4, what times itself gives you a negative? Will you ever have a number times a number give you a negative? Well, a positive times a positive is a positive, and a negative times a negative is a positive, so a number times itself will never be able to be negative. That's why it's imaginary, right? So the square root of 4 is 2, and because it's negative, we just put a little cursive I next to it for 2 imaginary. It's an imaginary 2. Because you can't really have a negative times a negative give you a negative, or a positive times a positive give you a negative. It doesn't really ever happen. So that's why it's imaginary, okay? So we have our reals versus our imaginaries. This you're not going to get into until Algebra 2 and on, but I kind of just wanted to let you know that, okay, so since there's reals, yes, there is fakes. We just call them imaginaries, all right? So real numbers, regardless of whether they are rational or irrational, have the following properties with respect to addition and multiplication. So the commutative property of addition, commute, like your parents commute to work. They drive to work. They move around, right? When they drive to work, they're moving. So the commutative property of addition is basically just saying that you can change or rearrange, move the order of the numbers that are being added. So if A plus B equals B plus A, all we did is we moved them around. The associative property of addition. So the associative property is basically saying that if B is dating A, and then B gets sick of A, dumps A for C, he's now associating with someone new. So his parentheses, his relationship was with A, and then he dumps A for C, and now he's associating with C instead. So those parentheses changed. He's associating with someone new. The associative property, you associate with your friends. Your groupings can change. Get it? Additive identity. The additive identity is 0. Anything plus 0 is itself. Additive identity, it's holding its identity. Anything plus 0 holds its identity. It stays itself. Additive inverse. Any number plus its opposite is 0. The additive inverse, any number plus its opposite is 0. Commutative property of multiplication. They commute to work, they move around. So A times B is the same thing as B times A. It doesn't matter when the order moves around. Associative property, you're associating with someone new. This is over addition this is over multiplication instead of addition. So B was with A, dumped A for C. He's associating with someone new. So you're going to do B times C before you multiply it by A. Here you did A times B and then multiplied by C. Multiplication is commutative. It doesn't matter which order you multiply the 3 numbers in, you will get the same answer. Multiplicative identity. Any number times 1 is itself. Any number times 1 is itself. Multiplicative inverse. Any number times its reciprocal is 1. So if I had 1/2 times the reciprocal, 2 over 1, I'd get 1. If I had 2/3 times its reciprocal, 3 over 2, I'd get 1. If I had 5/7 times 7 over 5, the reciprocal, the flip, then I'd get 1. Any number times its inverse is 1. Distributive property, you're literally just going to distribute it. So you have A times B plus A times C. So A times the sum of B and C is A times B plus A times C. You can just distribute that out. A set of numbers is closed under an operation if the result of the operation of any 2 numbers is in the set. Wait, sorry. Someone was asking me to go to the bathroom and I just lost my train of thought. A set of numbers is closed under an operation if the result of the operation on any 2 numbers in the set, provided the operation is defined for those 2 numbers, is another number in that set. To prove that the set is not closed under an operation, you need to find only one counterexample. Okay? Give a counterexample to show why the set of integers is not closed under division. Give a counterexample to show why the set of integers is not closed under division. Okay, so what if I did -5 divided by 2? I get -2.5, which is not an integer. Give a counterexample to show why the set of irrational numbers is not closed under multiplication. So square root of 2 is irrational, and if I multiply square root of 2 by square root of 2, I get the square root of 4, which is 2. right? 2 is not irrational. So an irrational times an irrational doesn't necessarily give you an irrational. State the operations under which the set of whole numbers is closed. Then state the operations under which the set of whole numbers is not closed, and give counterexamples to show why. All right, so for closed, addition and multiplication. Not closed, subtraction and division. So your counterexamples. One minus 2 is -1, which is not a whole number. And 1 over 2 is 0.5, which is not a whole number. Proving that a set is closed. Given that the set of integers is closed under addition and multiplication, prove that the set of rational numbers is closed under addition. Let A and B be rational numbers. A plus B equals P over Q plus R over S. P, Q, R, and S are integers with Q and S non-zero. S over S times P over Q plus Q over Q times R over S. Find a common denominator. Okay, so all they're doing right here is they're multiplying by S over S and multiplying by Q over Q. So they're going to get A plus B equals SP over SQ, RQ over SQ. So you're going to get SP plus RQ over SQ. Because PS plus QR and QS are integers, you're going to get a rational number. How do you know that PS plus QR and QS are integers? The set of integers is closed under addition and multiplication. So both expressions represent integers. Why does A plus B equals PS plus QR over QS prove that the set of rational numbers is closed under addition? Because A and B are any two rational numbers, and A plus B is also a rational number. The sum of any two rational numbers must be a rational number. Given the set of rational integers, given the set of rational numbers is closed under addition, how can you prove that the set of rational numbers is closed under subtraction? All right, so write a minus b as a plus negative b. If b is a rational number, then negative b is also rational. The rational numbers are closed under addition. So, a plus negative b is rational, because subtraction is adding a negative. An indirect proof starts by assuming that what you want to prove is not true. If the assumption leads to a contradiction, then the original statement must be true. So this is actually an indirect proof. This is actually part of geometry. We learn these in geometry. Proving that the sum of a rational number and an irrational number is irrational. Given that the set of rational numbers is closed under addition, prove that the sum of the rational number and an irrational number is an irrational number. Let A be a rational number. Let B be an irrational number. Let A plus B equals C. Assume that it's rational. Rewrite A plus B equals C as B equals negative A plus C by adding negative A to both sides. Because negative A and C are they're both what? Rational. And the set of rational numbers is closed under addition. Negative A plus C must be rational, which means that B is rational. This contradicts the condition that B must be irrational. So the assumption that C is rational must be false, which means that C, sum of the rational number and the irrational number, is irrational. An indirect proof is also called a proof by contradiction. What is the contradiction in the preceding proof? The number B cannot be both rational and irrational. Compare an indirect proof to a counterexample. A counterexample shows the statement is false by finding an example that it doesn't work for, right? An example that contradicts it. An indirect proof shows that the statement is true by providing that a contrary statement is false. Understanding radical and rational exponents. A radical expression is an expression that is written using the radical sign, a square root symbol, right? A radical expression has an index and a radicand, as identified below. So, how I always think of this is like the square root of 4 equals 2, right? Well, there's like an imaginary, the square root would be like 4 to the 1/2. So there's an imaginary 1 here and an imaginary 2 here. So it's a square root. It's what times itself, right? It's something times itself twice. So this is a 1 here and a 2 here. So this kind of helps me when I look at things. So like if I looked at something and it said like this, the cube root of 8. Well, the cube root of 8 is really 8 to the 1/3. If it would have been like this, then this would have been 8 to the 2/3. Does that make sense? So, looking here, square root and square root cancel each other out. Square root and square root cancel each other out. A to the k squared would be a to the k times a to the k, or a to the 2k. What are they doing here? Okay, they're just showing you that that's 2k, that there's an imaginary 1, so 2k equals 1, k is 1/2. They're just showing you that k is 1/2. So anytime square root is 1/2, anything to the 1/2. All right, guys, so explain why it makes sense that this is this and this is this. All right, well, if you cube a to the 1/3, you get a. Look, a to the 1/3 cubed would be a to the 1/3 times a to the 1/3 times a to the 1/3. When you're multiplying exponents, you add their exponents. So that's a to the 1/3 plus 1/3 plus 1/3 is a to the 3/3, or a to the 1st, which is just a. Make sense? Probably make this a little smaller. All right. The radicand of 3 rad a you get a, the radicand of 3 rad a. Okay. If you cube a to the 2/3, you get a to the 2/3 cubed would be a to the 2/3 times a to the 2/3 times a to the 2/3, which is a to the 2/3 plus 2/3 plus 2/3, which is 6/3. 6/3 is 2. A squared, right? 2, 4, 6 over 3 is 2. You get a squared. The radicand of 3 rad a squared. If the radicand expressions are rewritten in rational exponent form, you can apply the following properties to simplify them. The product of powers property. When you are multiplying exponents with the same base, you add the exponents. When you are dividing exponents with the same base, you subtract the exponents. A power to a power, you multiply, right? So if it's a times b to the n, that's the same thing as a to the n times b to the n. Power of a quotient property, you can distribute that as well, so a to the n over b to the n. Power of a power to a power, you multiply. So 2 to the 3rd to the 4th would be 3 times 4, or 12, 2 to the 12th, right? Power to a power, you multiply. Negative exponent property, a negative exponent is 1 over that number to the positive exponent. If it's in the denominator, make it positive, put it in the numerator. If it's in the numerator, put it in the denominator. Simplify each expression, assume all variables are positive. All right, so this is the same thing as x times y to the 6 over 3, or squared. That's the same thing as x squared, y squared. Okay, so square root of x times the cube root of x is x to the 1/2 times x to the 1/3. So you can add your exponents. 1/2 plus 1/3 is going to give you 3/6, so 3, 4, 5/6. The 5 goes there, the 6 goes there. X to the 1/2 over x to the 1/4 is going to be x to the 1/2 minus 1/4. Get a common denominator. 2 minus 1 is 1. X to the 1/4, there's a 1 there, there's a 4 here. The 4th root of x. In parts B and C, stated with an expression in radical form converted to rational exponent form and then converted back to radical form to record the answer. Explain the purpose of each conversion. So, the first conversion made it possible to apply the properties of rational exponents to simplify the expression. The second conversion let you write the simplified expression in its original radical form. Can square root of x times the cube root of b be simplified? Refer to the properties of exponents to support your answer. So that's the same thing as a to the 1/2, right? Times b to the what? A to the 1/2 times b to the square root. There's an imaginary 2 here and there's a 1 here, right? A to the 1/2 times b to the... Anybody? 1/3. Can that simplify? These don't have the same base, right? So no. They can't simplify because they don't have the same base. Right? You can't simplify them. They don't have the same base. Use the properties of exponents to prove that the square root of a, or the nth root of a times the nth root of b equals the nth root of a times b. Okay, so the nth root of a times the nth root of b is in rational exponent form, or in rational exponent form, is a to the 1 over n times b to the 1 over n. So then by the product property, AB would be to the 1 over n. Convert back to radical form to get the nth root of AB. Simplifying expressions involving rational exponents. All right, so 27 x to the 9th to the 2/3. So did they already simplify this? Oh no, okay. 27 is 3 to the 3rd. I'm trying to figure out what they were doing. 27 is 3 to the 3rd, and we're going to raise that to the 2/3. And then x to the 9th to the 2/3. We're just separating it out. They just did 2 steps in one because they changed the 27 to 3 to the 3. Well, if I have 3 to the 3 times the 2/3, those cancel out and you have 3 squared. If you have x to the 9th times 2/3, that 3 reduces this to a 3, leaving this with 6. Does that make sense? 9 times 2/3 is 6. 3 times 2/3, those 3's cancel out and it's 2. So 3 squared is 9, so this is 9x to the 6th. So that you get the same simplified form, if you simplify this, that is square this and then raise it to the 1/3. So square root of this, raised to the 1/3. Square this and then raise that to the 1/3. All right, well 27 squared well, that right there, to do it without a calculator, is 3 to the 3rd, right? Squared. X to the 9th squared. So that's really 3 to the 6th, x to the 18. And then to the 1/3, that'd be 3 to the 6th times 1/3, x to the 18 times 1/3, which is 3 squared, 18 to the 6th. Wait, 1, 6, x to the 6th. Wow, my brain is all over the place. X to the 18 to the 1/3, 18 divided by 3 is 6, which is 9x to the 6th. What is the simplified form of this? How is it related to the simplified form of this? All right, so the simplified form of this. Anything to the negative power is 1 over that number to the positive. So this would be 1 over 3 to the 3rd, x to the 9th, all to the 2/3. 3 to the 2/3 would be squared. 1 over 3 squared, or 9. 9 divided by 3 is 3 times 2 is 6, x to the 6th. So it would be the reciprocal, right? It'd be the reciprocal of the answer. They are reciprocals. Practice. All right, so go to page 334 and let's try a few. So I want you guys to try out number 5, number 6. Try 5 and 6 first. What did you guys get for 5? D to the what? What's the exponent? One-fifth. What about the next one? B to the what? 2/3. Try number 7. M to the 3/4. All right, so to do this one, the easiest way to think about this, you can put them into fractions, right? You could do like y to the third z all to the 1/3 and then distribute the 1/3. Or you could just think, how many sets of 3 can I take out? I can take out 1 set of 3. So it's either way, whichever way helps you guys think. But if you want to just do, okay, all this to the 1/3, then you'd have y to the 3 times 1/3, z to the 1/3. These cancel out, and I'm left with y. Z to the 1/3 is third root of z. So basically, you can think about this as, how many groups of 3 can I pull out? I can pull out one group of 3. It's gone. I pulled it out. There's not one group of 3 to pull out, so that stays. It's like over here. This is an imaginary 2. How many groups of 2 can I pull out with the x's? 2 groups of 2, right? I can't pull any y's out. Square root of 49. What's the square root of 49? 7. How many groups of 2 can I pull out with your x's? One group of 2, right? How many groups of 2 y's can I pull out? 2. And nothing's left inside. Isn't this the same thing as x to the 1/3 times x to the 1/4? When you're multiplying exponents with the same base, you add the exponents, 1/3 plus 1/4. Seven twelfths, x to the 7/12, or the 12th root of x to the 7th. Make sense? You guys see how I'm doing this? You have to use the rules. You have to memorize the rules and use them. So like on this next one, 3 times 12 is what? 36. X times 3x is what? There's 4 of them, x to the 4th, right? Square root of 36 is 6. How many groups of 2 can I pull out? 2 groups, right? X times x, how many of them? 4 of them. Or maybe I should just do this separate for you guys. Hold on, I'm going to do this separate. This is the same thing as x to the 1/2, y to the 1/2, times x to the what? X to the what? 3/2. Y to the what? Y to the what? 5/2. These are all being multiplied, right? So when you're multiplying exponents with the same base, you add their exponents. 1/2 plus 3/2 is how many halves? 4/2. 1/2 plus 5/2 is 6/2. 4 divided by 2 is 2. 6 divided by 2 is 3. X squared y to the 3rd. X to the cube root is x to the what? 1/3 over x to the what? What is the 6th root of x? X to the what? 1/6. When you're dividing fractions with the same, when you're dividing exponents with the same base, you subtract. X to the 1/3 minus 1/6. 1/3 minus 1/6. You have to have a common denominator. 1/3 is 2/6. Do you agree? 2/6 minus 1/6 is 1/6. X to the 1/6. Distribute this. 8 to the 2/3, x to the 3 times 2/3. What is 3 times 2/3? Those cancel each other out, right? 3 times 2/3 is 2. 8 to the 2/3, well, that's 8 to the 2/3, right? 8 squared is, what's 8 squared? 64. What is the cube root of 64? What times itself gives you 64? Isn't that 4 times 4 times 4? So the cube root of 64 is 4. So you're going to have 4x squared. Because the cube root of 64 is 4. And x to the 3rd to the 2/3 is x squared. If I distribute this 1/3, I'd have the cube root of 216, a to the 9/3, which is a to the 3rd. What times itself gives you 216? 6 times 6 times 6 is 216. 6a to the 3rd. You can do 216 cube root, and it gives you that 6. 6a to the 3rd. I want you guys to try number 15, number 16, try 15 and 16, take a minute. So on 15, this is 8 to the 1/3, x to the 6 times 1/3 over y to the 9th times 1/3, right? 8 to the 1/3 is the cube root of 8. What times itself gives you 8? 2. 6 times 1/3 is 2, right? 6 divided by 3 is 2. 9 divided by 3 is 3. 2x squared over y to the 3rd. X to the 1/4 over y to the 8/4. So you're going to be left with x to the 1/4, or the 4th root of x, over y to the 2nd. 8 divided by 4 is 2. Try number 22. Everybody should be trying number 22. (16 to the 1/2 is the square root of 16, which is 4. So this is 1 over 4 to the negative 1. Or sorry, 1 over 4 to b to the negative 1, right? Because negative 2 times 1 over 1/2 is negative 1. b to the negative 1 goes on top. So it's really b over 4, right? Because that's 4. 16 to the 1/2 is the square root of 16, which is 4. What times itself is 16? 4. 1 over 4. B to the negative 1 goes on top. B to the first. Right? That's negative 1. Negative 1 goes on top. So it's B to the first, or B, all over 4. Try 21. Four times negative 3/4 is negative 3. Negative 8 times negative 3/4, 6. B to the 6th over A to the 3rd. You get A to the negative 3, B to the 6th. The negative 3 goes on the bottom. So B to the 6th over A to the 3rd. If it's a negative exponent on the numerator, you put it in the denominator to make it a positive. If it's a negative on the bottom, you put it in the top and make it positive, right? Try 18. (12 divided by 4 is 3. 3 times 3 is 9. 12 divided by 4 is 3. Negative 3. Y to the negative 3 goes onto the top. So it's going to be x to the 9th, y to the 3rd. Is this making sense? Starting to click? You have to memorize the rules. Let's do 19. We'll do it over here. 4x squared over y to the 6th, all to the 1/2. So all you're doing is you're distributing the 1/2 to everybody. 4 to the 1/2 x. 2 times 1/2 is what? 2 times 1/2 is not 2. It's 1. 2 times 1/2 is 2 over 2, which is 1. 6 times 1/2 is 6 over 2, which is 6 over 2 is 3. 4 to the 1/2 is the same thing as the square root of 4. What is the square root of 4? What is the square root of 4? What times itself is 4? 2x over y to the 3rd. 2x over y to the 3rd. And that is everything for today's lesson on 6.2, which is rational exponents. I hope you guys enjoyed the lesson. Please like and subscribe and have a wonderful day.